Hello and welcome to the lesson for 7-1 in your textbook, Solving Systems of Two Equations. Today should largely feel like an algebra review, where we're going to go ahead and solve and analyze systems of equations graphically and algebraically. When we discuss systems, for now, they're largely going to be a group or collection of different line equations or perhaps parabolic equations, and we're going to learn how to solve for different solutions that satisfy both of the equations. And the problem set, which is on your chapter outline, I encourage you to work through all of it. I know it seems like a lot, but if you only want to do a review on the processes and methods, you can go ahead and end before problem 44, although afterwards those are some really great conceptual and word problems. Now let's go ahead and work through this quick review. All of these different methods of rearranging should feel pretty comfortable to you, where you're rewriting or you're solving for some equation algebraically, and to solve it, maybe there's more than one solution. And when you go through problem 4, to say that one line equation is perpendicular to another, perhaps there's a special product that is going to be the result of multiplying the slopes of the lines. So if you go ahead and hit the pause button, and you can hit play once the entire class has gone through the problems. Here are the solutions posted. In problem 1, you're just rewriting that line equation, which is provided to you in standard form, into a different type of form, slope-intercept. In 2 and 3, you should recognize that you can have multiple solutions that are going to satisfy that equation. And in problem 4, you should be able to recall that for two lines to be perpendicular, their slopes must have a product equal to -1. And then lastly, the writing might have been a little bit different, but to make an equivalent equation, all really you're doing is just you are scaling up the problem. You're not making the line equation any different, you're just providing it in a different form. So when we're dealing with different sets of line equations, we're describing a solution of a system. And as a solution of a system is where two equations in two variables, most often x and y, is going to be an ordered pair of real numbers that is a solution of each equation. And future topics, you may get complex or imaginary numbers, but mostly we're going to be dealing with real solutions. Now again, most of these topics are largely review. So I want to go through and work out several different examples and make sure you're comfortable with different methods of solution. So go ahead and work out this first problem. Feel free to work in partners, but solve this system using the substitution method. And if you need a refresher on what is the substitution method, it can be found in your textbook on page 568. So instructor, go ahead and please pause the video. Okay, so the solutions. Using the substitution method, you can go ahead and rewrite either one of those equations and substitute into the other. This is a lot like parametric equations, which we just studied. But when we go through, your solution should be one ordered pair. And if you wanted a different method to solve for it, you could rewrite each of those equations into slope-intercept form, punch it into your calculator, and find the exact location for where those two lines intersect. Now, if we are dealing with nonlinear systems, meaning we have certain equations that do not graph just a straight line, then we have to describe solving the system algebraically. And again, you can maybe see an apparent method where we can take one equation and substitute a value into the other. So to solve a nonlinear system algebraically, really it's just a specific type of substitution. So again, go ahead and pause the video and then hit play once the class is ready for the solution. Okay, so the solution for solving a nonlinear system. largely it is another method of substitution, just more specific. Right? And you have to make sure that you substitute in the correct order and that you substitute with the correct variable, making sure that no part of a equation is being lost when you are rewriting and substituting. And in this case, we can have two different unique solutions to the problem once we set up and solve for x, and then substitute those x values in and find the corresponding y value. Now, the elimination method might be new to you, or perhaps it's just been a couple of years since you used it. But I want you to go through and use the elimination method to solve this one. If you need a refresher on what is the elimination method, that can be found on page 571. So go ahead and pause the video, please, and hit play when they are solved. Okay, so to solve for this system using the elimination method, we have to arrange the equations in a certain way, and then we have to start multiplying the entire equation, just one at a time, until you end up with a situation where you can eliminate a certain variable, as long as the top equation and the bottom equation have coefficients that, when they would be added together, would be equal to 0. In this case, you can eliminate y and solve for x. When you solve for x, then you can substitute that into either line equation and retrieve your y value. Now, there's many different ways you can set up and solve these problems. This is just one way of doing it. You could have also worked to eliminate the x variable. Either one of those is completely acceptable. Now, this may be a giveaway in the title, but some systems have no solutions. So if we go ahead, and we're going to walk through this one together, but if we solve this system, and hopefully at this point you're writing this down in your notes, if you try to punch this in your calculator, you would find that the lines do not intersect. And if you try to solve the system using either elimination or even possibly substitution, you end up with some kind of statement. And if you worked it this way, then you would retrieve 0 equals 20, which we know is a false statement. Therefore, the system has no solution. And if you go ahead and rewrote these equations, you would find out that they're two separate line equations with different y-intercepts, but the same slope. So that should key you in to know that there is no solution or no exact ordered pair that's going to satisfy both equations at the same time. Additionally, and we'll walk through this one together, if we were trying to find infinitely many solutions, or in this case, this is just exemplifying finding infinitely many solutions. If you were trying to solve this system, again, either by rewriting these as slope-intercept form lines and putting them into your graphing calculator, or using substitution or elimination, you would find out that you can work your way down into a statement where 0 equals 0, and perhaps earlier you would find a different sort of true statement, but there's no exact description of what x should equal or what y should equal. And if you graph these two line equations, you would find out that they describe the same line. So what does that mean? It means that the system has infinitely many solutions. So you can go through, and any value that is found on either one of those line equations is going to satisfy the other system. You may also recognize, when you see the system set up in standard form, that the second equation has just been scaled up by a value of 3. So that concludes our lesson. I encourage everyone to continue working and practicing on this. You can use any method you'd like, as long as it's an open question. However, I expect everyone to be able to solve for these graphically by finding intercepts or by using elimination, as well as the substitution method. With enough practice, you'll be able to recognize when is the best time to use a certain method. So tomorrow we do have early release. I'm going to plan on discussing the rest of the chapter outline. We'll cover any questions from the problem set, and perhaps there will even be a target practice. So thank you for your attention. Thank you for paying attention to Substitute, and have a great day.